All right, good day, and welcome to the chapter on magnetism. So, this week we're going to look at magnetism and the magnetic quantities, and we're going to relate them back to our electronic quantities and start to build the foundation for exactly what happens in our alternating current, especially with our inductors, which will come in a couple of weeks. Okay, so let's go here. All right, so the idea of magnetism and electricity is they're so closely related that um, the basic knowledge of one or the other will just familiarize us with what's going on. So the magnetism, the definition of magnetism is it's the property of a material that enables it to attract pieces of iron. So magnetism is it's found in nature, right? Naturally, or it can be created with electromagnetic, or you can magnetize some materials. Um, and the original word came out of the ancient Greeks, who found that stones actually contain oxides. The Chinese called those leading stones, which later on they referred to it as loading stones or lodestones. Now, some of the ideas of magnetism here, and let me move my. Hold on. I want to move this over here so it's not in the video. So anyway, the term flux has the unit of a Weber and the symbol of phi, right? These are all Greek letters. And then the Weber, the flux density is beta, unit of Tesla. Magnetic force is the F, ampere turn, reluctance, and field intensity. Okay, so let's take some of these values and relate them to the um, electronics, right? So the magnetic force is like voltage, flux is current, and reluctance is resistance. So if we go back here, the flux is current, so this would be current. The magnetic motive force is voltage, and the reluctance is resistance. Hold on. Resistance. Okay? So in our electronics, the flux is the current, the magnetic force is the voltage, and the reluctance is resistance. So if you keep that in mind, that's how it's going to react, or the function. Now remember, in electronics, the current is the flow of electrons, the voltage is the force or the push, and then the resistance is the opposition to the flow of resistance. So the same thing is happening here with our magnetism. Now, another definition here is permeability is the ease with which a material can pass magnetic forces. Reluctance is the opposition to that flow of magnetism. And then temporary magnets are a type that easily loses its magnetic strength after the magnetizing force has been removed. So like there are some materials, some metals, that if you touch it with a magnet, so like say a screwdriver, if you take a screwdriver and you touch it with a magnetic resource, so like here on the end of my flashlight here, I have a magnet, so that you can see that magnetize it. And if you just touch this on the magnet, it will then become its own magnetic force. So let me get here. Here's a paper clip, and you can see that then becomes magnetized. So that's just that's what that's referring to, is that some devices can be temporarily magnetized. All right? Now, a residual magnetism is the amount of magnetism that remains in a temporary magnet, and it will wear off over time. So like in an hour from now or less, that screwdriver will no longer be magnetized. It's just temporarily. And then there are permanent magnets that are designed to keep a hold of that magnetism forever. And those are the ones that are found in our magnetic devices, such as our speaker systems or, magnetic lid. Like here I have my little Yeti coffee cup, and the little lid here has a magnet on there, and that's a permanent magnet, right? It doesn't lose its magnetism. All right. Now, popular theory of magnetism considers the molecular alignment of the material, and that's known as Weber's theory. Now, all magnetic substances are composed of tiny molecular magnets, each with a north and a south magnetic pole, and the two form a dipole, which means there is a north pole and a south pole. And if a magnet is split in half, each pole will have a north pole and a south, or each half will have its own north pole and south pole. So if you keep breaking a magnet in half, you just basically create smaller magnets. So that it's not like the north pole stays on the top half and the south pole stays on the bottom half. It changes. It develops it automatically. All right. Now, a more modern theory of magnetism is the electron spin principle. Now remember, think back to your DC class when we talked about the electron shells, right? The valence electrons, and how they, based on conductivity or how good a substance is as a conductor, the ones that have the free valence electrons are better conductors than the other ones. And the same concept here is, it seems to be associated with both spinning and orbiting electrons. All right? And there's some stuff in here that you can read chapter 16. I won't go through all of this. But some elements that are really magnetic have unpaired electrons that cause that strong magnetic field. Like, so ferrometic, right? Is the ferrous oxide is iron, right? That's why iron is the core of the earth is made of iron, and there's a huge magnetic pole, the North Pole and the South Pole, right, on the planet, that has a magnetic field. Okay? So iron has 4 unpaired electrons that with the same spin, and that this magnetic field is a vector, and it has both a magnitude and a direction. So here's the iron atom here, where you can see here's the nucleus here. Then the unpaired electrons, right, has 1, 2, 3, 4 of those. So when it comes in contact with another, with an electron or a magnetic substance, it's going to have that opposites attract and then the likes repel, right, which is a principle of magnetism. Now, another fact is that in material, atoms do not act independently, but are in groups, which are called domains. And they can be broken down when the temperatures increase. So if you superheat a magnet or a magnetic material, the groupings will break down, and like iron, and that's known as the Curie point, that's 770 degrees Celsius. So above this temperature, iron loses its magnetic characteristic. So if we go back to the Earth's core, in the core, there's that molten lava, right? A molten iron, where some of it is losing its magnetism because it's beyond the 770 degrees. All right. Now, unmagnetized materials can be magnetized if they're inside of the coils of a temporary magnet, which is known as an electromagnet. So here's the flux lines, right, that go. So we have the North Pole and then the South Pole of the magnet, and these lines go out and then come back in to the poles. So they just form a field around it. Now, the space surrounding magnet is the magnetic field. And if you sprinkle iron filings on a piece of paper and then or glass and put a magnet underneath it and just sprinkle them on there and kind of shake it a little bit, they'll form this. You'll see that the iron will get into those fields. It will automatically work out that way. All right. And we used to do a lab like that in the lab 27, which we skip because it's the iron filings and the magnets. You can see this. Now, if you go on YouTube, you can search for magnetic videos that will kind of explain it. And I'm sure some high school physical science teacher will show the iron filings. Okay? Now, with the magnetic fields, those are the flux lines. So these lines here, these are known as, these here are the flux lines. Okay? And remember, the flux lines represent the voltage, right? The or the magnetic force, or which is the flux lines, is the voltage. Okay, now flux lines can pass through. It's assumed that they go from the North Pole through to the space around, then come into the South Pole. And inside the magnet, the lines travel from south to north, thus completing the loop. So really what that's saying is, it starts to north, it goes around, and then it comes here and it completes the loop, and it just keeps circling. And that's magnetism. All right. Now, so here you can see them coming out of the north and going into the south and so forth. Now, another measurement for this is the Maxwell. And the Maxwell unit is equal to 1 magnetic flux line. And a flux line is also noted by the Greek symbol phi. And the Weber is a large unit of magnetic flux lines, where it represents 1 times 10 to the 8th, or almost a billion Maxwells. Right? There's not going to be any math on this chapter. In fact, this week's homework 3, is going to be basically fill in the blank. So if you read the chapter, you'll be able to fill those in real easy. All right. So here are some characteristics of magnetic lines of force. First, the lines of force are continuous and always form a closed loop. So they just keep going round and round and round and are continuous. And then the lines of force never cross one another. So if we look at these lines, they never cross. And if you do cross those lines with another magnetic force, it's going to produce a function in electronics known as induction. And that's going to induce a current, which is really important when we talk about inductors. All right, but that's the end of next week and the following week. All right, now parallel magnetic lines of force traveling in the same direction repel one another. If traveling in opposite directions, they unite or attract each other. So the principle of opposites attract and likes repel is true in magnetism. Okay, the lines of force tend to shorten themselves. Therefore, the magnetic lines of force exist between two unlike poles, cause the poles to be pulled together. And the lines of force pass through all materials, whether it's magnetic or non-magnetic. and magnetic lines of force always enter or leave magnetic materials at a right angle to the surface. So this right here, if this is the surface, this here is always going to be a right angle. So it'll come in and enter and leave at a right angle. All right. Now, if you've ever taken two magnets and try to push them together, depending on the strength of the magnet, you can't do it, right? They'll just slide off each other or repel each other at the last. So the strength of the magnet and the distance will do that. And this is a principle that's similar to Coulomb's law of electric charges, which is a principle of capacitors. So we'll explore that when we talk about capacitors in several weeks. Now, like magnetic poles repel, unlike attract, and the attraction or repulsion is directly or varies directly with the strength and inversely with the square of the distance between them. Now, the mutual attraction and repulsion of the poles produce a more complicated pattern than that of a single magnet. So if you have several poles, right, so the south poles are going to repel, whereas the north-south, they're going to attract. So these are going to try to slam to each other, and then the other ones are going to try to keep each other apart. All right, now iron, cobalt, nickel are ferromagnetic materials because they have a permanent, spontaneous magnetizing effect. This is caused by the spin of electrons and their magnetic moments. And its greatest, you have greatest magnitude at absolute zero, and then the least amount of magnetism at the Curie temperature. So that's where, in between those, you have the regular magnetism. Now, ferromagnetic materials are generally put into two categories: those with high retentivities and those with large permeability, initial permeabilities. So one's a hard magnet, one's a soft magnet. Hard magnets are called permanent magnets, and the soft magnets are more temporary. Okay? There's other materials or elements that can have magnetism, like aluminum, platinum, manganese are paramagnetic, which they have mild attraction, and then diamagnetic materials, which bismuth, antimony, copper, zinc, mercury, gold, and silver, they can be weakly magnetized. All right, you can have permanent magnets, which are normally made from hardened steel or some other alloy that includes iron, and it retains its magnetism even when the magnetism force is removed. So if you had an iron or a hardened steel that had a high percentage of iron screwdriver, and you magnetized it briefly just by touching another magnet, it'd retain that for some time. Now, you can lose magnetism through really high temperatures, physical shock, or any other strong demagnetizing force. So this demagnetizing force is known as a D-Gauss. So like in hard drives, right, magnetic, electric hard drives, the old hard drives, not the solid state drives, they use magnetism to maintain the data on the drives. And if you run them through a strong magnetic field called a de-Gausser, it will erase all the material on there. So a permanent magnet that you're probably all familiar with is the magnet in a speaker, right? So, and that is going to have a coil and then a permanent magnet. And when the electrical signal goes through the magnetic field, it's going to vibrate, and then that cone will produce sound. So that's how you can hear, even if you have your earbuds and you put it in your ear, that's still a small electromagnetic that's in there, that's taking the current from your device, which is then sent via Bluetooth to the receiver, and then it vibrates and you can hear it. And then the strength of the signal determine the volume of the sound. All right? So you can make temporary magnets with just a iron that's magnetized, and then it normally will demagnetize once it's taken away. Now, really soft iron has low retentivity, but if you use a steel mixture, right, which is steel and which is iron and other alloys, it has a very high magnetism. All right. Now there are other things that are part of this magnetism that are important. So here, if you just take a nail, a steel nail, and you wrap it in a coil and then apply a voltage to it, this will become magnetized. Once you remove the voltage, now the voltage is flowing, the current is moving through here that is going to induce a magnetic field. And then once you remove the voltage, the magnetism goes away. So if the current to the coil is controlled by a switch, then the magnetism produced can be turned on and off. And this is a common application for this is lifting magnets, buzzers, bells, and relays. So a relay is just a device that will temporarily open and close. So let me just open something here. All right, so like here is a common factor or look at a relay. So like here's a relay here that when it's, so you just energize it and it'll close, and then it's just like a magnetic switch. Okay, so that's very common in electronics. All right, so here's our voltage, and then we can use the 12 volt relay here. We'll close this switch, which will then induce a magnetic field here that will close this relay, and then our AC will flow through our circuit. So this is like our on-off switch that we can use with just with voltage. So we close this switch, then it energizes this electromagnet, which pulls down this relay that closes this switch here. All right, another common application is the tape recording. So particles of iron oxide coat mylar tape. The recorded head is an electromagnetic coil that produces a magnetic field proportional to the current, and then the flux preferential travels through the core, and then when it's read, the read-write head will pick up the signal there and then amplify it through the circuit. Right? Hard drives are going to use magnetism, and it depends on the polarity of the magnetic field. It's either a 1 or a 0, so it's in binary. So here's the read-write head here, and then this is the platter that has the iron oxide on it, and then of course the spindle and the motor and all that stuff. And that's how the hard disk works. Okay. Now ferrites are non-metallic materials that exhibit ferromagnetic properties of iron. They have very high permeabilities, but less than that of iron. And they're commonly used as magnetic cores, and they're used at high frequencies above a gigahertz. Right? You can also have magnetic insulators. So although you can't stop it completely, if a non-magnetic material, so one of the examples I like to use for this is if any of you guys have ever, or if any of you have ever watched the TV series on AMC, the Breaking Bad, right, with Walt and Jesse. And remember, they have the hard drive that Hank has in evidence, and they know that they're on film that was recorded on the hard drive from Gus's Hermano Chicken, right? The Chicken Brothers. And they go and they build that huge electromagnet in the back of a van, and they go to the evidence area where the laptop is, and they turn it on, and it erases all the data on there. That's like, there's no way to prevent that, even though you can shield from some EMI, right, with braiding or anything like that. But if it's electromagnetic, it will pass through whatever it is. So that can cause problems. All right. Now, the current passing through a coil also creates a magnetic field. So, and we'll explore this more when we look at the capacitor and the inductor in a couple weeks. And remember, the magnetomotive force is similar to voltage. So that's the pressure that forces the flux to move. All right. Reluctance is the opposition to the flow, which is resistance, and so forth. All right. So that's pretty much a look at magnetism in a nutshell. And then the last section here is with the flux density and magnetism force. If it's graphed, this is known as a hysteresis curve. All right. So where you have saturation in the magnet, that's point A. Where you have saturation in the opposite direction, that's point D. Retentivity, coercivity, and different flows here are on this curve. So the relationship between the quantities of the flux density, which is the B, and the magnetism force is the H, is this hysteresis curve. All right. Now, the hysteresis characteristic of a magnetic material, the magnetizing force is provided by an AC current, which by nature is reversing periodically, right? It goes positive, goes negative. It's plus minus, plus minus. So it's constantly changing. And remember that the rate of change is known as the frequency. So the greater the frequency, the greater the friction between the dipoles changing direction. So on this hysteresis curve, this A and this D are switching if it's induced with an alternating current. And that will cause the heat to come into the material. So the faster the magnetizing forces changes, the greater the hysteresis effect. All right. So that's chapter 16 in a nutshell. And remember, on Thursday in lab, I want you to turn in homework 2 and then pick up homework 3. So that's what we're going to do going forward is, now that I have your homework 1, I'll have that graded and I'll give those back, or you'll be able to pick them up on Thursday. When you turn in homework 2, you'll pick up your graded homework 1. And then I'll make a short video where I'll go over all of the homework. So if you missed anything or if you were unclear, I want to make sure you have a video of me going over that. All right. And then, of course, you want to pick up your homework. That will be homework 3, which will be due at the beginning of week 4's lab. All right. So hopefully that clears up chapter 16. I hope you're doing well. If you have any questions or comments, feel free to reach out to me either with the Ask the Professor forum on Canvas, the inbox on Canvas, my email which is kmiller30@mountsac.edu, or via phone call. All right, that's it, and I will talk to you later.